Industrial analysts looking ahead to 2026 are describing a structural crisis that could stop the production of high-resolution displays in its tracks. For decades, the simple act of touching a screen has defined our relationship with machines. We moved from specialized peripherals like keyboards and mice to an interface that responds directly to human contact. This interactivity relies on an atomic-scale coating called indium tin oxide, or ITO. It is a conductive material embedded in the glass that detects the bioelectricity of your finger and translates it into a digital command. Because this layer is invisible, the industry has treated it as an infinite resource. But recent supply chain data suggests this material bridge is starting to fail. To understand why, you have to look at how we get it. There is no such thing as an indium mine. You cannot simply dig a hole to find more of it when demand for smartphones spikes. Indium makes up only 0.052 parts per million of the Earth's crust. It is a byproduct metal, found almost exclusively as microscopic traces inside the zinc mineral sphalerite. This creates what economists call an inelastic supply. As this chart shows, the demand for displays is exponential, but indium production remains tied to the global demand for zinc. If the construction and automotive sectors don't need more zinc, the world doesn't get more indium. This geological bottleneck is concentrated in a single market. China currently controls approximately 70% of global refined indium production. In February 2025, China introduced new export licensing requirements for indium. This administrative move slowed the flow of the metal to international manufacturers, effectively triggering a supply deficit. Because production is structurally capped by the zinc market, there is no way to dig our way out of this shortage to meet the needs of the electronics industry. When primary mining reaches its limit, the industry turns to urban mining, trying to harvest indium from the millions of devices we discard every year. The problem is that recovery requires stripping microscopic traces of metal from complex, multi-material components. The indium is locked in ultra-thin coatings on the glass, not found in solid blocks that are easily sorted. Recovery requires hydrometallurgy, treating shredded electronics with concentrated acids to dissolve the metals, followed by solvent extraction to isolate the indium. The chemistry is so difficult to scale that 90% of the indium used in consumer electronics is lost during the product lifecycle. Inefficient collection and the complexity of the extraction process mean that only 10% ever returns to the supply chain. Because the ITO layer is so thin, it is currently cheaper to process tons of raw zinc ore than it is to recycle old screens. We are effectively burying the material needed for future screens in landfills. The combination of restricted mining and inefficient recycling has led to a manufacturing crisis. In early 2026, the shortage began to impact the physical output of display factories. As Indian prices rose toward $400 per kilogram, global factory utilization plummeted. Manufacturers were forced to slow down production lines just to manage their remaining inventory of coating materials. This shortage impacts more than just phones. It threatens the build-out of 5G telecommunications networks and the production of thin-film solar panels, both of which rely on indium-based compounds. The limit on this single material has created a ceiling for hardware innovation, ending the era of cheap, scalable display technology. To move past this bottleneck, the industry is shifting toward alternatives that don't rely on indium. The leading alternative is silver nanowires. Unlike the brittle ITO used in traditional screens, these nanowire networks are flexible, allowing for foldable and bendable devices. While these materials can be manufactured using printing techniques, scaling this new infrastructure is now a race against the depletion of the current indium supply. It is a sharp reminder of the physical reality behind our digital habits. We built a global culture around the sense of touch while remaining largely unaware of the specific dust that made it possible. We designed a world that responds to a tap, but if we can't solve the chemistry of the material itself, we may find ourselves reaching out to screens that can no longer feel us.